Hello friends, today we will be comparing alkanes, alkenes, alkynes and arenes. In this video, we will be talking very basic, simple, important from examination point of view related to alkene, alkene, arene and alkynes. So you can say we will be today comparing aliphatic hydrocarbons not only with aromatic but with each other, such as alkane, alkene, alkynes also. In this video, we'll be starting with very basic things related to alkane, alkene, alkyne, and arenes. See, here I'll be explaining this alkane, alkene, alkyne, and arene in a very simple way so that it will be easy for you to remember from examination point of view. See, a teacher can make your topic an understanding one, easy one, or by his method of explanation, he or she can make it complicated one or beyond your approach. See, the first thing there in entrance examinations or board examinations that you should overcome your nervousness. Learning and recalling what you learned there in your sessions is not so easy. But be relaxed, be calm, be composed, then only you can recall all such things. See, as I told you, today we'll be comparing alkane, alkene, alkyne, and arene. Or you can say today our topic is very basic idea about the hydrocarbons. In this video, we'll be discussing about the introduction of these hydrocarbons, what their general formula is, what will be the percentage S character in these different hydrocarbons carbon will be having, and what hybridization carbon will be showing in all these compounds, what will be the bond length, bond angle, and bond energy of all these compounds. See, the very first thing about these hydrocarbons is their general formula. See, the general formula of alkane is CnH2n plus 2. What does it mean? See, this C₂H₆ is ethane. In this C₂H₆, the graphical formula of this ethane will be like this. This is condensed molecular formula and this is graphical formula which was given by Cooper. Now see here how many carbons are there? 2 carbons are there. So N is equal to 2. Then H2 into N, as we have already said, is 2. So 2 2s are 4, 4 plus 2, 6. So C₂H₆. Now see alkene. Alkene, that is C₂H₄. What this C₂H₄ is, that is ethene. What will be the graphical formula of this C₂H₄ is? This will be its Cooper's graphical formula. Now see here, what the meaning of N for this ethene is 2. So C 2. Here also n is equal to 2. So 2 into n, what n is? 2. So 2 into 2 will be 4. This is what we have written. Now see, what is the meaning of general formula for alkyne? Means now see here C₂H₂, that is ethane. Now see here what the value of n is 2 and H is 2 into 2, that is 4. 4 minus 2, that is 2. So here what will be its graphical formula, Cooper's graphical formula? It will be like this. Now see, what about arene? Arene, in case of arene, minimum number of carbon atom will always be greater than or equal to 6. Less than 6 carbon atoms in arene is not possible. That is aromatic hydrocarbon. Now see, if we take N as 6, so C6, H2 into N, 2 into 6, that is 12. 12 minus 6 will be 6. This is benzene. This is benzene. What will be its graphical formula? Its graphical formula will be like this. This is carbon, 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 all the 6. This ring is having carbon atoms. Now see, here I'll show you its graphical formula. H, here also H, H, all the 6 carbon atoms will be attached with hydrogen atoms through single bond. Now see C6 and H also 6. Now see the valency of each carbon atom. So I'll start with this carbon. 1, 2, 3, 4. 1, 2, 3, 4. All carbon atoms will be having valency 4. And as you know, the valency of hydrogen is 1. So in this way, you can write the general formula of these different hydrocarbons. Now see what the next property of these alkanes, alkenes, and hydrocarbon is. C. Hybridization of carbon shown in alkane will be sp3. How we can say it is sp3? See, you wrote ethane like this, or any alkane. It can be ethane, methane, propane, butane. All cases, carbon-carbon single bond will be there. Here, carbon-carbon single bond. Here, carbon-carbon double bond. Here, carbon-carbon triple bond. This is the basic difference. Here, one carbon will be having one single bond and one double bond. So alternate single and double bond, we can say they are in a cyclic manner there in case of arenes or aromatic hydrocarbons. And one such example of arene or aromatic hydrocarbon is benzene. Now see, in this case, this one carbon will be having 1, 2, 3, 4 sigma bonds. How many sigma bonds? 4 sigma bonds. Since number of sigma bonds will be 4, so hybridization shown by this carbon will be sp3. See, in hybridization, plus charge will never be counted. Free electron will never be counted. Pi bond will never be counted. In hybridization, only lone pair will be considered, sigma bond will be considered, and negative charge will be considered. Positive charge, never. Free electron, negative. They will never be considered. They will never be. What is the meaning of considered? Means will never be counted for calculating this hybridization. Since here 4 sigma bonds, each carbon is having, this carbon is having 1, 2, 3, 4. This carbon is also having 1, 2, 3, 4 sigma bonds, 4 sigma bonds. So hybridization will be sp3. Now see, come to this alkene. The first example for this alkene is ethene. Now see here in this case, 1, 2, 3. 3 sigma bonds. In this carbon also, 1, 2, 3. 3 sigma bonds are there and 1 pi bond. As I already told you, pi bond will never be considered there in the hybridization. Plus charge, free electron and pi bond will never be considered. Only sigma bond will be counted there for calculating this hybridization. So 3 sigma bonds. So since 3, what is the meaning of 3? 3 means sp2. What is the meaning of 3? 3 means sp2. 3 means sp2. Now in alkyne, this is the graphical formula for alkyne. Each carbon is having 1 and 2 sigma bonds. There in this ethine, 1 and 2 sigma bonds. 2 sigma bonds means sp. 2 sigma bond means sp. Since it is having 2 sigma bond and 2 pi bonds, as we have said, we will never consider a pi bond there in their hybridization. But see, in resonance, sigma bond will never be considered. Pi bond will be considered. Plus charge will be considered. Free electron will be considered. Lone pair will be considered. Minus charge will be considered. But in resonance, sigma bond will never be considered. This is what the difference between hybridization and resonance is. In resonance, pi bond will be considered, and in hybridization, sigma bond will be considered. In hybridization, free electron will never be considered. Positive charge will never be considered. But in resonance, free electron, positive charge, lone pair, minus charge, all will be considered. This is what the difference between resonance and hybridization is. See, this is what the important points related to your examination from this hydrocarbon is. Now see, this arene will be having alternate single and double bond. Now see here, double bond, single bond, double bond, single bond, double bond, and each carbon will be having one hydrogen atom attached with it. In this way, you'll draw its structure, you'll draw its graphical formula given by Cooper. Now see here, in this case, this one carbon will be having 1 sigma, 2 sigma, 3 sigma. Like this, every carbon will be having 3 sigma bonds. 3 sigma means sp2. So in arenes or in aromatic hydrocarbons, first example for it is benzene. Their hybridization shown will be sp2. In this way, we have discussed general formula. We have discussed hybridization of this alkene, arene, alkyne, and alkene. Now see what the next property related to this is. As you have said, sp3. So 1 is S and 3 is P. Total is 4. Out of 4, S is 1. Out of 4, S is 1. So 1 upon 4 into 100. So what it would be? It would be 25%. C, this hybridization will be deciding the percentage S character. And on the basis of percentage S character, you will be deciding oxidizing power, acidity. Acidity means tendency of losing hydrogen, covalency, etc. So many properties which are very crucial there in organic chemistry from examination point of view will be decided by this percentage S character. Now see here, total is 3. 1 is S, 2 are P. So total is 3. Out of 3, S is 1. So 1 by 3 into 100. If we calculate this percentage, what we will get? We will get 33%. So the percentage S character there in alkene is 25. There in alkene it is 33. And there in alkyne, 1 is S and 1 is P. So 1 S out of 2 total and multiplied by 100, what you will get? You will get 50%. Here, as there in case of alkenes, it was 33%. Here also it will be 33%. See, more the percentage S character, more the percentage S character, more will be the oxidizing power or oxidation number, more will be the covalency, more will be the acidity. Since here this is most covalent. Why? Because here percentage S character is 50 and this will be least covalent because here percentage S character is 25. This will be most acidic. What does it mean? It means if we'll take alkyne and that alkyne will react with sodium or with any metal or base, then this will be losing hydrogen most easily. This hydrogen will be lost most easily and this hydrogen will be lost with most difficulty. Means alkyne will lose its H atom, or you can say will be most acidic in nature and alkane will be least acidic in nature. This is what the meaning of percentage S character is. Oxidation number will be very high, or you can say oxidizing power will be very high, and covalency will be very high, acidity will be very high. In some other topic, this percentage S character will be deciding around 17, 18 properties, very important there in organic chemistry, so that we will discuss some other day about this all. And from examination point of view, again and again I am saying, is very crucial, is very important. What does it mean? Important means probability of asking question from there is huge. So from that point of view, it is very important. Now see, this next property related to this alkane, alkene, alkyne, and arene is CC, or you can say HCC bond angle. HCC bond angle. What will be the bond angle and what will be shape? In alkane, shape will be tetrahedral and bond angle will be 109.5 degree. In alkene, shape will be planar. This is alkene now. So the shape will be planar and bond angle will be 120 degree. In alkyne, it will be linear. This is linear shape and bond angle will be 180 degree. And arene, since in arene also hybridization shown is similar to alkene, so their bond angle and shape will also be same, that is 120 degree and planar in shape. Now see what next property related to these alkanes, alkenes, alkyne and arene is CC bond length. Bond angle is over. Now it is bond length. CC bond length. See here in alkene, CC bond length will be 154. In alkene, it will be 134. And in alkyne, it will be 120. That is there in picometer. 154 picometer, 134 picometer, 120 picometer, and this arene, their CC bond length will be greater than alkene and lesser than alkene. So lesser than 130, sorry, greater than 134 and lesser than 154. Reason is resonance. Since in this arene, alternate pi bonds are there, so we'll be showing resonance. There will be delocalization of these pi bonds, and because of that, their bond length will be greater than alkene and lesser than alkene. So in between alkene and alkane, bond length of CC bond there in arene will be there. Now see what next is. Next property related to this is CH bond length. CH bond length in alkene, alkene, alkyne, and arene. In alkene, CH bond length is 112. In alkene, it is 110. In alkyne, it is 106. And in arene will be greater than this alkyne and will be lesser than this alkene, that is 109 picometer. See, like this, we'll be doing some other properties related to this. Hydrocarbon is. Now see what next property related to this alkene, alkene, alkyne, and arene is, that is bond energy. Now see, this bond energy will be written there in kilojoule per mole. This is Cc bond energy. In case of alkene, this bond is the weakest bond because there is no pi bond, only sigma bond is there. So 348 kilojoule will be per mole will be the Cc bond energy there in alkane. Now see, you says that pi bond is weaker than sigma bond, but that is additional bond. Na? Sigma bond is here also, but here sigma bond, in every case sigma bond will be, since the first bond, so will always be there. But one more additional bond is there. Of course, that is not so strong as alkane as sigma is, but so what? That is additional bond. Na? So this is 348, this is 681 kJ per mole, and here two additional pi bonds will be there. So 823, that is 823 kilojoule per mole, and in arene, it will be lesser than alkene, but greater than 348, that is 522 kilojoule per mole. So that's the point. Now this was about the Cc bond energy there in kilojoule per mole is. Now see, next is CH bond energy in kilocalorie. See here, this was kilojoule per mole, and this value I am writing there in kilocalorie per mole. You know, 1 calorie is equal to 4.18 joule. 1 calorie is equal to 4.18 joule. So calorie is a bigger unit than joule. There was a question there in iitjee. There they asked you about the order of the value of energy, units of energy. Calorie is the biggest, then joule, then erg is the smallest value of energy, smallest unit of energy. So in this way, you can calculate the different units of energy, which one is smaller, which one is bigger. So here in alkenes, alkenes, alkynes, and arenes, in all the cases, CH bond energy is same, that is 99 kilojoule per mole. That is 99 kilojoule per mole. Now see, these were the few properties of this alkane, alkene, alkyne, and arene. We have compared them. Now all these properties, what we studied today, are here. We have written all these properties together so that you can remember all of them easily. Thank you very much for your valuable time. All the very best for your coming examinations. Thanks.